Einstein says that space and time have a geometry. They have a life of their own. They have dynamics.
Those dynamics are what we call gravity. The more dense the region of matter, the greater the gravity, the deeper the curve. This connection is the foundation of our physical reality.
It's the interaction between matter and energy and space-time that created the universe that we see around us today.
But that doesn't mean we fully understand it.
There's much more that we don't know, and that's frustrating. With the laws of physics, I can talk about how space-time behaves, but it does appear to be something that stretches, that contracts, and that gravity is the embodiment of space-time.
Born in the Big Bang, space, time, and energy combined to create our infant universe. These basic materials were the foundations. But how did we get to the incredible, complex structures we see today? How did space-time build our majestic cosmos? Our entire universe was created in the Big Bang 13.8 billion years ago. Everything came from nothing. But our modern universe is a complex mosaic of matter.
When we marvel through our telescopes at the fantastic structure of our universe and its galaxies, you gotta ask, where did that come from?
Matter in the universe arranges itself on a vast cosmic web. Galaxies and galaxies clusters are strung out on sheets and filaments.
It seems this intricate web is organized by a cosmic architect. Space-time. It shaped everything, from planets to galaxies, atoms to cities.
The universe is made of space-time. Whatever the substance is, time and space bound together, that's expanding and creating the universe we see around us. It's everything. Space-time is what the universe really is.
It's a hard concept to grasp, and even harder to visualize. Scientists observe the universe in different wavelengths of light. This is the sun, invisible light, X-ray, and ultraviolet. Now imagine if we could see it in the space-time spectrum. We would see space-time distorting as objects move through it.
Space-time can warp and push things around. It can expand and pull things apart.
But it's the shape of space-time that dictates how we experience it.
Imagine you're in your car. You go up hills and you go down hills. So the shape of Earth's surface determines how you travel across Earth's surface. In the same way, the geometry of space-time determines how light and matter move through space-time.
The rules are simple. Matter, in fact, any object, tells space-time how to curve. The curvature of space-time tells matter how to move.
Because the shape of space-time tells matter how to move, what we call gravity, this means that gravity and the shape of space-time tells matter how to clump together and form larger and larger structures.
But at the beginning, the space-time landscape was very different from today's. And the very first matter started to change the shape of space-time.
So this space right here has a tiny bit more matter in it than this over here. Wherever there was a little bit of extra mass, that would bend space a little bit more. Well, if you're bending space a little bit more, then more mass would collect there.
In the early universe, the denser regions of matter created deeper curves in space-time.
And as the mass gets bigger, as stuff falls into that well, it gets deeper and deeper and deeper and attracts more stuff. And it's just a runaway process.
Gravity increased, pulling in more and more matter.
Got more dense, got more dense, got more dense, and then before you know it, you've got a star, and you've got a bunch of stars, and you start to make a galaxy. And these stars evolved and began forming large structures. They sort of burned through all their nuclear fuel and exploded, and they made all the heavier elements. And with time, we got down to having things like planets, atmospheres, people, all the things that we care about today.
All of this started out as energy fluctuations in expanding space-time.
These, at first, very tiny fluctuations became these gigantic structures that we actually see today.
And over billions of years, that material began to coalesce into individual galaxies, stars, planets, and you.
Fluctuations in the expansion of space-time laid out the pattern of the universe. The curvature of space-time controlled the evolution of everything we see today.
If space-time didn't have that property of bringing mass together, then all we would be is a thin haze of hydrogen gas. Not a very interesting universe at all.
If space-time didn't curve because of matter inside of it, the universe would be a really weird place. I mean, there'd be no gravity. There'd be nothing to make things stick together.
No force of gravity means no stars, no planets, and no people.
We owe our existence to space-time. But even scientists struggle to understand it.
I wish I knew what space-time is. We know things about space-time, but at the same time, we feel like we know almost nothing about space-time.
Then, in 2015, we caught a break. And for the first time, we heard ripples in space-time, generated by one of the most violent events in the history of the universe. The universe is filled with space-time. We think it's been around from the beginning of everything, quietly pulling the strings of the cosmos. And sometimes we get a glimpse of this elusive puppet master in action. 2016, astronomers witness a strange optical phenomenon. A weird circle of light, like a cosmic halo.
This is actually what you would see in the sky if your eyes were as sensitive as a telescope. They're real. This is not some artifact of how we adjust the images. Something is actually bending space and time itself into a lens.
That something is a red galaxy, which is over 7 billion light years away from Earth. It's bending the light from a blue galaxy, which should be hidden behind it. It's called gravitational lensing.
Gravitational lensing is an amazing phenomenon because it demonstrates explicitly what Einstein told us, that space is curved. And space acts like a lens, just like the lens in my glasses acts. And when we look out at the universe, we see all of that. It's remarkable.
Mass from the foreground galaxy creates curves in space-time, which we know as gravity. Light follows those curves and is warped, so it bends around the galaxy.
Massive objects, like clusters of galaxies, can bend the path of light through space-time, a lot like a piece of glass can bend the path of light. So when we look at a distant galaxy, as the light passes through a galaxy cluster, we see multiple images of the same galaxy. We see arcs and circles, as if that galaxy cluster were made of glass. We are seeing the warping of space-time literally played out in front of our very eyes.
Gravitational lensing gives us a way of seeing the effects of space-time on light. But it's only an indirect observation of space-time. Could there be another way of experiencing space-time right here on Earth?
Not everything that happens in space can be seen. Sometimes you have to listen for it as well.
believe it or not, space is a material much like this iron sheet. And like this iron, space can distort. If I put a very heavy weight on this sheet of metal, its shape is going to change and it's going to distort. Amazingly, space can carry waves, and so can this iron sheet. But to get this sheet waving, you need something really powerful. Something like me and my hammer. Did you see those waves travel through that iron sheet? Well, waves pass through space in exactly the same way. We call these gravitational waves.
Gravitational waves are vibrations from cosmic events transmitted through the material of space-time.
To set off waves in space, you need the biggest, baddest, most powerful events in the universe. Something like the collision of two black holes.
When two black holes collide, the energy released sends shock waves through space-time across the universe. By the time they reach Earth, they're so small, they're immeasurable. Almost. In 2015, scientists at the LIGO Observatory made a groundbreaking observation. They detected ripples in space-time, gravitational waves.
Rumors began flying, but it became clear after a while that this was indeed the first direct detection of gravitational waves seen by man-made instruments on the Earth.
When we discovered gravitational waves, it had been so long that we'd been waiting for signals. Not only did most of us not believe it, I went so far as to be so skeptical as to look into all kinds of conspiracy theories for ways it could be fake.
When I saw this data, I still think back on it now, and the emotional impact it has on me. The only thing comparable is when I saw my daughter's face for the first time after she had been born. It was that kind of an emotional impact, just having all of this thing that we had worked for coming to fruition in one moment. It's mind-blowing.
We can actually hear these gravitational waves on Earth.
Part of what makes this so amazing, it's a bit of a coincidence, but it's a really cool coincidence, is that the signals that LIGO actually measures are in the same frequency band as the sounds that the human ear is sensitive to.
We can hear the waves change frequency as the two black holes get closer and collide.
It's a swoop up in frequency that sounds like whoop.
What we were hearing in that whoop were two black holes that are orbiting around one another and then coming together. That was it.
Listening to ripples in space-time has given us a powerful new tool to investigate the universe.
We are now hearing things in gravity for the first time. It's a sense that we have never been able to apply to the universe, and we're beginning to learn what is out there.
The observation of gravitational waves from black holes is one of the most significant findings in astronomy by anyone in the recent 100 years.
It's hard to overstate the importance of gravitational wave astronomy. Much like when Galileo first pointed his telescope at the stars to see something new, we now have an entirely new window into the universe.
Gravitational lensing and gravitational waves offer us an insight into the complex relationship between gravity and space. But what about the other half of the equation? Time.
But it turns out, it's space-time. Gravity not only distorts space, it actually distorts time, too.
We think of time as something that can't be changed. It simply flows ahead at a constant rate. But that's not the universe we find ourselves in.
In some crazy circumstances, my time might even, according to you, stop.
It might even be possible to travel through time and go back to the future. For sci-fi fans, space is the final frontier. For scientists, exploring time is a much bigger challenge.
Originally, we thought of time as the same thing as the sun rising and setting. But now we've come to realize that time is a more fundamental concept than that.
Time isn't just something that passes. Time is an essential part of our universe. It's part of the fabric of space-time. The Big Bang was the beginning of space and time. Since then, space has been expanding and time has been ticking forward. It's been doing this for 13.8 billion years, creating the universe we see today.
Space and time are tied together. They're the same thing.
So when matter influences space-time, it's not just creating deformations in space, it's also affecting the flow of time.
This is where space-time becomes really cool.
Just as gravity bends space, it also distorts the flow of time.
This isn't how we perceive time. This is actually the rate at which time flows.
Very massive objects can warp and twist space-time itself. So not only is space distorted, but time itself can slow down or even stop.
The stronger the gravity, the greater the distortion.
What has the most gravity? A black hole.
Out in space, near a strong gravitational tug from a black hole, clocks can do funny things, and this is where things start getting really interesting.
Around a black hole, space-time warps and twists, slowing time down. Scientists dream of sending a probe there to test their hypothesis.
There's a famous way of thinking about this called the twin paradox, where two twins are born at exactly the same time, right? So they're the same age, but one of them zips very, very close to a black hole, hangs out a while, and then comes back.
If I had an identical twin who stayed back on Earth while I flew near a black hole, when we had our daily video phone calls, he would see me go, "Hi there," and I would see him say, "Oh my goodness, I'm a little bit concerned about you because you're talking so funny." We would literally notice that time is running at a different pace for the other one.
The closer to the black hole, the slower time passes.
If instead of coming back home, I accidentally fell backwards into the black hole, my twin back on Earth would see me slow down even more. I'd go, "Oh!" and completely grind to halt and seem frozen on the event horizon.
Time appears to stand still.
I would just have a sinking feeling that I would never be able to come home again.
But if the twin could escape from the black hole, he would be returning to the future.
Maybe it's only been a few days or weeks experienced by the one that traveled to the black hole, while the other is, gray-haired and has grandkids by now, has lived decades here on Earth.
The black hole warps space-time so much that the ultimate science fiction fantasy becomes reality.
Time travel is a staple of science fiction, and we know that time travel into the past appears to be ruled out in our universe. But time travel into the future is totally acceptable.
Time travel isn't possible just yet, but space-time has a very real effect on our daily lives. It controls how we age.
The key to different rates of flows of time is gravity. If you experience a different gravitational environment, you will have a different flow of time. As I climb up these stairs and I put myself further away from the mass of the Earth, my own clock runs a little bit faster. If you go down closer to the surface, the more your clock slows down. We have sensitive enough clocks that we can measure this different flow of time.
Exaggerate this effect, and we would see the flow of time change in front of us. Those closer to the Earth would look slowed down. Those higher up, the opposite. Which means the wealthy in their penthouses actually would age faster than people on the ground.
This is a mind-blowing concept, but it's reality.
Earth's gravity even controls time high above the planet. 12,500 miles up, there's an array of global positioning satellites, crucial to the navigation systems in our cars and cell phones.
We here on Earth use the global positioning system as a way of getting around. Okay, most people these days would be lost if they have to go more than about 1 kilometer from their house unless they have their GPS app on their phone to tell them where to go.
The GPS receiver in your cell phone bounces signals over 4 satellites to figure out exactly where you are. It's an exercise in precision timing. On board each satellite is an atomic clock. The weaker gravity in orbit means the satellite clocks tick fractionally faster than those on the ground.
If we didn't know to correct for the fact that the clocks in our satellites move at different rates, the GPS system here on Earth would not work.
It would actually lose accuracy at such a rate that the entire global positioning system would become useless in less than an hour. We correct for that every moment of every day.
Space-time has controlled every phase of the universe's evolution since its birth. Now, we're discovering space-time will also dictate how the universe will die. Our universe started with a bang, 13.8 billion years ago. It's been expanding ever since. Will this expansion last forever? Or will our universe come to a violent end?
For almost 100 years, we've now known that the universe is expanding.
Everything in the universe is expanding away from everything else.
We can test this by measuring light from exploding stars. Type 1a supernovas all explode with the same brightness, so scientists can accurately work out their distance from Earth. For decades, astronomers have measured this light being stretched by expanding space-time.
The universe is expanding, and there's matter in it. That matter has gravity, and that is distorting the curvature of space-time.
So it made sense to us that as the universe expanded, all of the matter in the universe would hold on to each other gravitationally.
If there's enough matter in the universe, it can actually pull on itself enough that the expansion gets slower.
But in 1998, astronomers took new measurements and made a sensational discovery.
People had expected it to be slowing down, to decelerate, but instead they found the opposite. The expansion is accelerating.
If expansion was slowing, then these distant lights should seem brighter. Instead, they were dimmer. They were getting farther away, much faster than expected. It could only mean one thing.
That expansion is getting faster. It's accelerating every day.
This discovery turned our understanding of the universe upside down.
For the first 7 billion years of the universe, the rate at which the universe was expanding was going slower and slower. But then something crazy happened. It was as if gravity had become the opposite. Instead of attracting the galaxies, it was almost as if it was pushing them apart.
That's a very surprising result. We're still struggling to understand it.
Was gravity losing its power? Or was there something else pushing space apart?
There's another ingredient in our universe, an ingredient that behaves very oddly.
A mysterious quantity called dark energy.
Like space-time, dark energy is all around us. We can't see it, but it makes up 70% of the stuff in our universe. But what is it exactly?
Dark simply means that we have no idea what it is. We don't know what form it is in. Something is pouring energy into the universe, causing it to accelerate.
We don't know what it is.
No clue whatsoever.
We don't have the slightest explanation. It's the biggest mystery in science today.
Dark energy behaves in mysterious ways.
Ordinary matter is attractive. Dark energy is repulsive. That's why it's causing an acceleration. Ordinary matter feels gravity, it comes together, but this stuff doesn't.
Is dark energy a new force in the universe? Or, like gravity, could it come from space-time itself?
Dark energy may very well be a property of space-time. It may be that space itself has an energy, and it's this energy that's driving it to accelerate in its expansion.
Dark energy is a thing. We don't really know exactly what it is, but it will have a huge effect on the future changes in the universe.
So what will happen if dark energy keeps accelerating the expansion of our space-time universe?
Because of the presence of dark energy, it'll expand faster and faster and faster, which means the universe is going to become a lonelier and lonelier place to be.
All the galaxies are accelerating away from each other. The universe gets dimmer and dimmer and colder.
Everything gets darker and more desolate, and right now that is the leading candidate for what's going to happen in our future.
Eventually, our space-time universe freezes.
The Big Freeze is the ultimate endgame of the universe as we know it. It is an ugly fate. It's a depressing fate, but luckily for us, it's not until an unimaginably long time from now.
Trillions of years from now, the universe could end in a big freeze. But a 2017 study hints at an even more frightening possibility. Dark energy might be getting stronger.
One horrible scenario for the ultimate fate of the universe is if dark energy eventually grows so strong enough that it can overwhelm the gravitational attraction of a galaxy itself.
It's even able to rip black holes apart.
The very fabric that holds everything together could be ripped apart. This idea is called the Big Rip.
First clusters, then galaxies like our own Milky Way will be torn apart. Then our solar system will break up. And in the final half hour of the universe, the Earth will explode. In the final second, atoms will vaporize.
Everything in the universe would individually be torn apart by the expansion of space.
We don't understand dark energy. Is it constant? Is it getting stronger? Is it getting weaker? At this stage, we simply don't know.
The future of our space-time universe hangs in the balance. Will it end in a big rip? A big freeze? Or is the end really just the beginning? Space-time controlled the birth of our universe. It will also dictate its death. Now we're discovering these two events may be linked. A link that reveals a flaw in our understanding of the Big Bang.
Everything we can now see, all the matter, all the energy in our universe was once contained in a region smaller than the size of an atom.
We call this tiny, infinitely dense point a singularity. Singularities are predicted by the general theory of relativity. But the universe is also governed by another set of rules: quantum mechanics.
Quantum mechanics is our description of the subatomic realm, of fundamental particles and fields and forces and how they interact.
Quantum mechanics says that nothing can be infinitely small or dense. So singularities can't exist.
Singularity is a bit where everything kind of goes to hell because the densities become infinite, gravitational forces become infinite, things just sort of break down there and the equations sort of stop making sense.
No singularity would mean no Big Bang as we understand it. So then, how did the universe spark into existence? Scientists now think they have an answer. A solution that works with both general relativity and quantum mechanics. Quantum space-time.
A successful theory of quantum spacetime should answer the question of what really happened in the earliest moments of our universe.
Hopefully, the correct quantum theory of gravity won't have any singularities. It will replace the Big Bang with something else. If we only knew what that something else was, we might have a clue as to how and why the universe began.
In a quantum space-time Big Bang, there was no singularity bursting from nothing. The universe formed from the remnants of another dying universe.
It's possible that before the Big Bang there was still a universe, there was still space and time, but rather than expanding, the universe was contracting.
Perhaps universes don't end in rips or freezes. Perhaps they collapse. An ancient universe expands, but then begins to collapse under its own gravity, crunching space-time down to a speck. But instead of forming a singularity, space-time once again explodes.
As matter gets more dense, then as the matter crunches down, this force will push everything back out.
The universe would bounce and reignite in a new round of expansion, a new Big Bang.
What we perceive as the Big Bang is the aftermath of that bounce.
This suggests that the space-time that dictates our lives today comes from the collapse of an old universe. And we live in an infinite space-time cycle of birth, death, and rebirth. A bouncing space-time universe.
If we live in a bouncing universe, it's very plausible the universe is infinitely old, that it's gone through an infinite series of bounces, and there is no absolute beginning.
It could be that we are just one iteration of an infinite number of cycles in the lifetime of some meta-universe.
We barely understand space-time. Perhaps we will never understand it completely. But one thing is clear. Without space-time, we would not be here.
Space-time is something absolutely real. It's really part of the fundamental architecture, the furniture of reality.
To really understand the ultimate fate of our cosmos, it's not enough just look more with our telescopes. We also have to understand the basic nature of space-time.
You really are right now living in a far more complex and beautiful universe than the human mind can comprehend.
For thousands of years, planet Mercury has baffled astronomers. But now, its secrets have been revealed. It's a bizarre world unlike any other.
When you look at the family of planets that make up our solar system, Mercury does seem to be a little bit of a weirdo.
This is one tough world, surviving brutal attacks from comets, the sun, and even other planets.
You can see by the surface of Mercury that it has a lot of battle scars. The solar system did not treat it well.
And yet, this world has been brought to life with water ice, volcanism, and tectonic activity.
If I had to describe Mercury in a word, it would be surprising.
At first, it may seem that you could write this off as a dull little dead rock close to the sun. But Mercury has a story to tell.
And this story could end with Mercury threatening the very existence of planet Earth.
Ignore it at your peril, because there may come a day when Mercury makes its presence very well known indeed.
The Messenger spacecraft completes its final orbit around planet Mercury. And the images sent back to Earth during its mission left scientists stunned.
Our view of Mercury from before and after the Messenger probe is like having terrible vision your whole life and then finally going to the optometrist and getting glasses that clear everything up. And it completely opened our eyes to what this planet looks like.
Mercury orbits the innermost solar system, the closest planet to the Sun. Around 3 times closer than Earth. In a scorching environment of lethal heat and radiation. Capturing images was a monumental challenge for the Messenger mission team, led by Sean Solomon.
Mercury has been among the most difficult planets in the solar system to study. The Hubble Space Telescope is forbidden from viewing planet Mercury because it's too close to the sun and their optics would be severely damaged.
Messenger looks closer than we ever have before. It reveals a strange world, just 5% the mass of the Earth. Closer in size to our moon.
At first glance, Mercury and Earth, they're nothing alike, right? They're both made of rocks. That's about it. They're both orbiting the same sun. But when you start looking a little bit closer at Mercury, you start seeing some really surprising similarities to Earth.
When scientists look at Mercury, they spot something that shouldn't be there.
Mercury has water on it, which if you were to make a long list of all the discoveries about Mercury, I think water would be right at the top of what? What? Seriously?
If you thought in advance of the last place in the world to find water, you'd think of Mercury because it's so close to the sun.
It gets even stranger. The water exists in the form of ice. There could even be 1 trillion tons of it, enough to encase Washington, D.C. in a frozen block 2 miles thick. So how do you get frozen water onto the closest planet to the sun?
For me, I think the most interesting thing about Mercury is the fact that what should be the hottest planet in the solar system is in some parts among the coldest. And I love that paradox because I love the unexpected.
Mercury is a world of brutal extremes. The sun-facing side is blasted by solar radiation, with temperatures rocketing to 800 degrees Fahrenheit, hot enough to melt lead. But the side facing away plummets to minus 300. It's all because of Mercury's almost non-existent atmosphere. Planetary scientist Dan Durda demonstrates the effect this has using a campfire.
So right now, with this jacket on, holding the warmth in, I'm a bit like a planet with an atmosphere. The atmosphere of a planet, it's a thermal blanket, a thermal insulator that helps make more uniform the temperature of the entire planet. So at the moment, I'm pretty warm uniformly, but if I take this, if I take my jacket off altogether, well, you know, I can already feel my back cooling off. Sitting here without my jacket, without an atmosphere, if you will, I'm like the planet Mercury, which has no effective atmosphere, and therefore the only warmth that it can hold is the warmth radiating directly on it from the sun itself. Any parts of Mercury facing away from the sun very rapidly radiate that heat off to space and cool to very, very chilly temperatures.
So, could water ice survive on the side of Mercury facing away from the sun?
The nighttime side is very bitterly cold. If that were the end of the story, you might be able to have, you know, frozen water, icy water on the side of Mercury facing away from the sun. But Mercury doesn't keep one side always locked to the sun and one side always facing away. It actually does rotate. It rotates 3 times for every 2 trips it takes around the sun.
As Mercury turns, the sun would vaporize any water ice facing it. But are there secret hiding places where the sun cannot reach? To find the answer, planetary scientist Nina Lanza searches fissures in Iceland.
So here we can see at the surface, there's no ice, it's too warm. But if we look down in this fissure here, it's only about 20 feet deep, but at the bottom, there's actually some ice. So if we measure a rock that's been in the sun, let's say this one, we can see it's actually pretty warm. It's about 61 degrees Fahrenheit. But if we aim now for the bottom of this hollow, what we can see now, it's about 33, no, it's dropping. It's 32 degrees Fahrenheit. And this is because the sun doesn't really get to the bottom of this place. And that's the key.
While this ice is hidden in a fissure, on Mercury, the ice survives in craters on the planet's north pole, forever safe from the glare of direct sunlight, because these craters sit in a perfect spot.
Mercury's axis doesn't tilt very much compared to the sun. The Earth's axis tilts about 23 degrees, but Mercury is pretty much straight up and down. And that means that as large as the sun is in the sky, there are craters on the poles that sunlight never gets to. They're always cold. So the surface of Mercury is heated and then cooled as it moves around the sun, but there are craters that are always dark and always cold.
Against all the odds, despite everything that suggests this shouldn't happen, Mercury is a safe haven for this water ice.
The bottoms of these craters are called cold traps because they're so cold that any water that gets there stays there basically forever, can last literally for billions of years. But where would it have come from? It probably came from comets and asteroids. Comets are giant chunks of ice. So if a comet hits Mercury, that's going to deliver a lot of ice. And in fact, we know a lot of asteroids have ice on them as well. So both of these things could deliver water to Mercury.
Comets and asteroids brought water ice to the innermost planets of the solar system. This same water delivery system gave Earth the elements needed for life. And though Mercury has pockets of frozen water, the planet can never use it to develop living organisms.
What Mercury is really showing us is that you can start with the same basic building blocks for planets, right? You can have essentially the same materials, but end up with very different environments.
Compared to the other planets, Mercury ended up as the runt of the litter. But there's evidence this wasn't always the case. Could this little world have once been much, much bigger? We have theories for how the planets first formed in our solar system. But Mercury just doesn't fit in.
When you look at the family of planets that make up our solar system, you know, Mercury does seem to be a little bit of a weirdo.
On Earth, we have a relatively small core and a thick mantle and a thin crust. So you compare the core of the Earth to the size of the Earth, it's relatively small. If you look at Mercury, it's not that way at all. The core is absolutely huge compared to the planet itself.
Mercury's huge iron core is surrounded by an unusually thin mantle of rock. It just looks odd.
It's funny, you don't expect to get a core that large in a planet that small.
It's almost as if Mercury lost some of its mantle somewhere. I mean, maybe it left it behind the couch. Who knows? But it's gone now.
But how can this material just vanish?
Mercury could be the way it is now, because it started as a much larger planet, and then something happened to strip away the top layer of it. And the only way we know how to do that on a planetary scale is with planetary impacts.
Picture the early solar system, when Mercury is still forming. It's completely different from the little world we know now. Up to 4 times more massive, twice the mass of Mars. But it orbits in a shooting gallery. Impacts are inevitable. And before long, an object the size of our moon smashes into Mercury in a giant impact event.
This is apocalyptic. This is the sweatiest nightmare you can have. You're resurfacing an entire planet. The energies are vast. One of these giant impacts probably would have remelted it all the way through. What's going to remain after it's done is completely different than what started in the first place. It's hard to overstate just how impactful these events are.
Huge chunks of Mercury's mantle are flung into space. The result? 2/3 of its mass are now made up by its core. But where did the rest of it go?
Billions of years ago, there was a planet that we will never know. A planet that was destroyed when the current Mercury was formed. Is it possible that some of it may still be out there?
The lost mantle debris could still exist in the innermost solar system. Scientists call these hypothetical objects volcanoids.
Volcanoids can be very valuable for understanding the formation of Mercury, because some of these volcanoids may be pieces of Mercury's missing mantle.
But in order to survive, these volcanoids would have to orbit on a gravitational tightrope.
You know, like this marshmallow, volcanoids exist in a kind of a precarious position in the solar system. A little too close to the fire, a little too close to the sun. Those objects actually would vaporize away. Kind of like that. If you orbit too far from the sun, you're going to approach too closely to Mercury, have gravitational encounters, maybe get flung out of the solar system, or maybe just impact Mercury itself and get eaten, if you will. But in between those two extremes, at just the right distance from the sun, a little closer to the sun than Mercury, but not so close that you get fried, is this volcanoid region where objects in orbit around the sun could remain gravitationally stable over the entire age of the solar system. That's the place to look for this potential population of little asteroid-like objects.
We know where they should be, but there's a problem.
You may wonder why haven't we seen these volcanoids if they actually exist? If they're actually orbiting, why don't we just look for them? Well, it's because they're really close to the sun.
Unlike the asteroids or the Kuiper Belt objects, where we're looking out away from the sun, from our perspective here on the Earth, we're looking out into the dark nighttime sky. In the case of the volcanoids, we're looking for something very, very close to the sun, in close to that really brilliant light source.
Our sun is around 900,000 miles across. Mercury is just 3,000. When our telescopes see Mercury passing in front of the sun, it's little more than a pinprick. With volcanoids, we're searching for something thousands of times smaller than Mercury. If volcanoids exist, they orbit in a blind spot. But scientists will keep searching for them, because they could be the last surviving remnants of Mercury's lost mantle.
If we were to discover volcanoids, that would offer us an entirely new population of objects to study. This material could offer some rather unique insights into the formation of Mercury itself.
A giant head-on impact has been our best explanation for Mercury's weird structure. But now, there's a startling new theory for Mercury's missing mantle. It was stolen. But who is the thief? Now, there's a startling new theory for Mercury's missing mantle. It was stolen. But who is the thief? We assumed that Mercury lost most of its mantle in a giant head-on collision. But the Messenger spacecraft turned everything on its head.
One of the exciting things that we've learned about Mercury recently, by sending probes to study its surface, is that its surface is littered with material that we didn't think should be there, things that we'd call volatiles.
The volatiles are chemical elements, like potassium. They're called volatile because they evaporate easily in high temperatures. Just the sorts of temperatures generated by a giant impact.
If I had to describe Mercury in a word, it would be surprising. The idea was that a smaller object ran into Mercury and knocked off material. Well, that actually would work to make it lose material, but it would also generate a lot of heat. And because of that, the volatile materials on Mercury would also have been lost. But today we see that they're still there.
So it meant that most of the basic scenarios that had been laid out for how Mercury was assembled had been disproven. We had to go back to the drawing board and rethink how Mercury was assembled and how Mercury evolved.
How did Mercury lose its mantle, but retain these volatiles?
Mercury is like a detective case. We have the body, we have some clues, but we really have to piece it together.
Planetary scientist Eric Asborg tackles this giant riddle.
The original idea was that Mercury was hit by something smaller than itself. But whatever process made Mercury somehow preserved all these volatiles that should have vaporized and gone.
Eric has a bold alternative. A hit-and-run collision.